Well, the prizes aren't why we do this research. We do this research to figure out what our universe is at the very fundamental level. So what is it we found out using this enormous machine? I want you to imagine the fabric of space-time without space or time, just as an empty, four-dimensional fabric with absolutely nothing in it at all. Now imagine the flow of time appearing in this fabric. When you do this, you have to choose some arbitrary direction to be the flow of time. It works a lot like this. If I take this arrow and I balance it on the stage on its tail as perfectly as possible and let it fall, it's unstable, and it falls in some arbitrary direction. This is the process of symmetry breaking. This arrow chooses one specific direction, and now this sets a direction over the entire stage. Now I can say, walk 2 arrow lengths from here and turn, and here I am. It sets a direction and a sense of scale. And this is exactly the way symmetry breaking works in our universe to produce the direction for the flow of time. And now, in our universe, after symmetry breaking, I can say, proceed 14 billion years from the Big Bang, then turn perpendicularly from time into space, and travel to a pale blue, insignificant planet in the Milky Way galaxy, and here we all are. But time doesn't travel smoothly in all directions throughout space-time. We know it's bent by matter. Right now, the Earth is bending the flow of time towards its center, and we feel this as gravity. Right now, as all of us are traveling forward together in time, our temporal flow is being bent towards the center of the planet. And the only reason we're not all accelerating downwards right now is we're pushing against our chairs. So not only can the flow of time bend, but it can also ripple. This is called a gravitational wave. And we think it's created by the motion of very dense, very large chunks of matter. But what is this matter stuff? The way the universe works, we think, is that every point of space-time, there is another internal space with many dimensions that are perpendicular to our 3 dimensions of space. Right? So this is not an internal space that's in our space, but rather attached to it and moving over it. Now, for each different direction in this inner space, there's a corresponding different kind of elementary particle that can exist at a space-time point. Now, we don't know what the complete shape of this inner space is, but we do know what parts of it are. And one very important part of it are the 4 dimensions corresponding to the Higgs field. I can describe what that looks like with this ball. So if you imagine this beach ball, the surface of it, to be a perfectly symmetric 4-dimensional shape, right? That what happens is via symmetry breaking, one direction you have to choose is special. All right? And then this is called the Higgs direction. And this is very similar to how the flow of time becomes special in space-time. But here we're dealing with the internal space of particle physics. Now, once you have this direction picked out, this happens at every point over space-time. So now, this uniform field over space-time with the Higgs direction picked out is what we call the Higgs background. And just like time can ripple, this Higgs field can also ripple. A ripple in the direction of the Higgs field over our space-time is what we see as a Higgs boson. This is the particle that gets popped into existence that corresponds to this wave in the Higgs direction over space-time. And this is precisely what we were able to create for a brief and glorious moment at the Large Hadron Collider. We popped these particles into existence. They immediately decayed into other particles, which we tracked and cataloged their properties, and were able to determine that, yes, we had a Higgs boson there created for a brief moment. It was a spectacular achievement of science. Now, to actually understand now how this validated theory describes how particles get mass, you have to understand how this Higgs shape twists around the inner space of elementary particles. So what do I mean by that? Well as that four-dimensional shape, we have another shape in there corresponding to the electroweak force. Describe it with this two-dimensional pool floaty. One direction around here corresponds to what's called weak charge, and the other direction corresponds to what's called hypercharge. And the Higgs direction is not uniform over this electroweak torus in this internal space. It twists around it. All right? Now, this corresponds to the charges of that Higgs direction. So, although this geometry is very complicated, all you have to do is count the number of twists. There are 3 twists around the hypercharge direction, 1 twist around the weak charge direction. You go and you make a very simple plot. But this is precisely how the symmetry gets broken of the electroweak force. Perpendicular to this Higgs direction is what we call electric charge, which makes an angle called the weak mixing angle. And this electric charge is made of part hypercharge and part weak charge. Now, all the other elementary particles we know of that can exist also twist around this electroweak torus. And we can plot them according to their twists here on this plot and see their charges. Here are the 3 components of the Higgs field and how they twist around here. The W bosons. And the photon and the Z naught don't twist. They're parallel around this torus. So they sit in the center of this diagram. The electron has 4 different parts. Its left and right part, and the particle and antiparticle. And same for the up and down quarks, and probably the neutrinos. So this diagram of twists is the fundamental pattern of elementary particles in our universe. It's a complete diagram of these charges. There are other particles you may have heard of, such as the bottom and top quarks, but they have the same number of twists as the up and down quarks, so there are a lot of overlaps here. Now, you can rotate this diagram by the weak mixing angle, and now see how the Higgs particle interacts with all of these particles to give them their mass. So the Higgs direction, when you add the Higgs to the left-handed part of the electron, it turns into the right-handed part of the electron. So what's going on at every point in our space-time when there's an electron is it's there bouncing back and forth between its left and right-handed parts interacting with this Higgs background, and that's how it gets a mass. And this happens for every other kind of massive particle. And this is how we end up with the elementary particles we see. Now, as well as the electroweak torus inside this inner space, there's also another torus corresponding to the strong force. And there's also a hyperbolic torus corresponding to gravity, but I wasn't able to find that one as a pool toy. Turns out they take forever to inflate. But if this is the strong force, then the quarks also twist around this torus, and they make a wonderful pattern of twists. It creates a triangular pattern of a charge that because it came in a triangle, we called it color charge, and labeled the quarks according to their charge as red, green, and blue. And the gluons also twist around this strong torus, and these are what carry the strong force. And when they interact with the quarks, they change their color. And this is what binds all the quarks together inside the atomic nuclei. And this is how all the matter we know of in the universe comes to exist. 2 up quarks and a down quark make a proton of total electric charge +1. A down quark and an up quark and 2 downs make a neutron with 0 electric charge. These clump together, bound by the strong force, orbited by electrons, bound by photons, and we see everything around us in the universe. All of this described as a beautiful, complex twisting of geometry. It's really a fantastic picture. Now, as I said, we're not sure what the complete space is yet of internal particle physics. But I do have my own guess for what this is. This is the most beautiful possible internal space known to mathematics. It's called the E8 Lie group. And it just so happens that all the charges of all the known particles in physics match charges in this geometric structure. It's a fantastic thing, and this is what I work on. It also happens to look really good on a t-shirt.